Oh, okay. First, I would like to thank the organizer for the invitation. It's really a great pleasure to participate in the workshop. So today I will tell you some of our efforts trying to understand basic behavior of moiré heterostructures. As you have, everyone here knows that by putting two atomic thin layered material together, you can form these moiré superlattices. And if you think about these moiré superlattices, they give us basically periodic structure that allow us to create basically artificial quantum solid. So at the very beginning, the first order of approximation people will have is these artificial lattice can be thought of Harvard model with strong correlations, and that can give rise to all kinds of model physics or maybe even topological physics. But if we think about real materials, actually what make a quantum solid or kind of extremely rich is when you have a single unit cell, you don't consider it as basically a position for a single electron that can occupy. Instead, within a unit cell, they can actually be all atoms, and the changes of potential landscape for electrons and holes in the system. And furthermore, for a single atom, you can have many electrons rather than a single electron. So those electron-electron interaction within the single moiré unit cell can actually lead to even more complex behavior. So what we were trying to ask is whether in a moiré superlattice we can also consider related effects, like what's the effect of a complex potential landscape that will affect electrical as well as optical behavior, as well as when you have multiple electrons in a moiré unit cell, how do they arrange and behave that can be different from a conventional solid. So I'll briefly talk about three topics. The first one is talking about the potential landscape and its effect for the electronic ground state. So for example, how a charge transfer insulator or multi-insulator can compete with each other. Then the second part, I will talk about the potential landscape, which can be different for electrons and holes. How do they affect excited state, in particular moiré excitons? And last, I will talk about when you put multiple electrons in a moiré unit cell, how these single particle levels compete with electron-electron interaction, and it can give rise to Wigner molecular crystal states. And many of these studies will actually or be based on scanning tunneling microscopy, actually motivated by Ken Shi's first work showing actually STM really gives you a very powerful tool to study the microscopic behavior. So the first example we'll look at is the WS2, WSE2 moiré heterostructure. This is a STM image where you can clearly see the topography of these moiré superlattices. And it was actually first pointed out by Liang Fu. So when you look at the effective potential, the moiré potential for electrons is actually not just a single position where the electron can live in or the hole can live in. Instead, the potential for electron hole within a moiré unit cell can actually have a rather complex potential landscape. In particular, very often you can actually have two valleys with relatively close energy for electrons. So in that case, when we see insulating behavior, when with one electron per moiré unit cell, which has been indeed observed experimentally previously, there are actually two possible understanding of these correlated insulators. If this potential difference between different values are very large, then the band gap of this correlated insulator state, as illustrated here, will be determined by the Coulomb repulsion energy for double occupancy on the same site. On the other hand, like what Liang Fu showed, if this kind of the potential energy for kind of the two values are very close, then the second electron would actually like to go to a different position rather than occupy the same position. In that case, it is known as a charge transfer insulator, where the gap is determined by the basically potential energy landscape rather than the Coulomb repulsion energy on the same site. So the question is, for example, in this specific WSE2, WS2, how does this on-site Coulomb energy compete with kind of a potential difference at different sites, and what really determine the gap of this correlated insulator? Or to answer that question, we turn to scanning tunneling spectroscopy of this heterostructure. So on the left-hand side, we just show basically an image where the STM will measure a gated sample. On the right-hand side, we plot the DITV curve as a function of bias in the horizontal axis and the gate, which is doping the system in the vertical axis. So you can see there is a large tunneling current for electron hole band, and there is a large gap in between. But I would like to draw your attention is in addition to this overall broad signal that's associated with density of state, there are also these very sharp lines, dispersive lines as pointed by those, that red arrow, the blue arrow. So those actually corresponds to something known as charging discharging event, when you use STM to study a strongly interacting like a semiconductor. So to understand these illustrations like this, assume initially we have this correlated insulator where you have one electron at per moiré site. And when you bring the STM to do your spectroscopy, you basically will apply a bias to the STM. And that bias will accumulate some charge, and it will actually push, basically exert a force on this charge. And when the force is large enough, it can discharge an electron and leads to a sudden change of electron configuration and also a sudden change of tunneling current. And with that jump of tunneling current, you see at the IDV peak. So the telltale sign of this charge, discharging event can be actually seen by looking at the mapping of this discharging event, because discharging is coming from a basically capacitive coupling between your tip and your kind of a charge. Then the discharging basically will happen as a ring type of fashion. And in particular, this ring will expand if you use a larger voltage, because if you have a larger force, you would be able to push the electron away when the tip is further away. And that's indeed what we see experimentally, and that tells us those dispersive lines are indeed discharging peaks. So here we just show that you see this discharging ring that are expanding when you use a larger tip bias. And the center of this ring basically tells us where the electrons are or where the holes are. So in this case, I think we are looking at hole band. So we can see the first hole is sitting at the BSEW side. So then we can ask what will happen when you put two electrons or two holes in the system. So are they sitting on the same site, which is predicted by a multi-insulator, or they are sitting at two different sites, which will be predicted by a charge transfer insulator? So this is now we change the gate voltage to put two holes per lattice site. And when we increase the tip bias gradually, you can see first discharging is actually happening at these blue circles. And when the bias voltage is large enough, then the second discharging event will happen, characterized by those green circles. So this is a direct kind of real space image telling us the two holes we put in the system are actually sitting at two different sites. So this is a charge transfer insulator where the second hole is sitting at this BWS site, where you can discharge it first with a small tip bias. And then the first hole is sitting at BSEW site, where you need to use larger force to discharge it. And by modeling this system, we can estimate this kind of the effective gap energy is about 90 millieV. Or we can also compare it to on-site Coulomb interaction. We found they're actually rather comparable, but in this specific system, the potential energy differences are a little bit smaller. So in general, in different TMDs, these two competition actually can be rather subtle and can depend a lot on the detailed experimental or material system. Okay, so what I've shown you, the potential landscape can change the behavior of the ground state of electrons. We can also ask what will it change the behavior for excited state, for example, excitons. So in that case, like Aline has mentioned, it turns out in kind of TMD system, the potential minimum for electrons and for holes can be at different sites. So in that case, when we create an electron hole, there are actually two competing effects again. If the electron and hole are not interacting with each other, basically they would like to be localized at separate positions within a moiré unit cell. On the other hand, all the electron and hole do have a strong attractive Coulomb interaction. So in that case, they want to form a tightly bound excitons. So in the early literature or theoretical understanding of moiré excitons, people usually think the excitons tend to be strongly bound, and the moiré potential will just provide a small perturbation. But when we start to look at the magnitude of the electron and hole moiré potential, again, we found that energy scale and the Coulomb energy is really comparable. You really need to treat them with equal footing. And in particular, Steve Lewis' calculation showed that in many TMD heterostructure, actually, in some cases, the potential difference between the electron and hole at different sites can overcome the attractive Coulomb interaction of these electron and holes. So in that case, they can lead to a somewhat unusual and rather unique type of exciton for moiré heterostructures, where the electron and the hole are delocalized at different sites within our moiré superlattice. So the question is, so can we actually observe them in real space to really visualize these charge transfer exciton? So to do that, we want to find a system where this electron hole potential landscape is particularly deep, so they can easily overcome the kind of electron hole Coulomb interaction. So we'll realize basically kind of a charge transfer exciton at the lowest energy state. So based on calculation, it turns out twisted HOMO bilayer is best for those situations. Or as mentioned by different people now, like different HOMO bilayer actually behave rather differently. So we found for the, if we just want to see a very, very deep potential and also have large effect between electron holes, the twisted bilayer WS2 with close to 60-degree twist angle is the best. So on the left-hand side, I just show you the structure of this moiré heterostructure. And then what we'll do is we'll shine light onto the system and probe where the electrons and holes are. So first, let's just confirm the electronic band structure. So if we look at the valence band, we found the lowest energy for the valence band are strongly localized at this AB stacking site. And then if we look at the conduction band, we found the conduction band are strongly localized at this BWW site. So in that case, the electron hole indeed prefer to sit at different positions within the moiré unit cell. And then if we shine light to the system, we can measure the tunneling current. So the yellow curve shows before shining light, there's a large band gap. So within the gap, you have very little tunneling current. But once you shine light, you can actually see there's a significant tunneling current even within the gap. This is basically a photocurrent generated by the laser excitation. And if we then measure the photocurrent as a function of position, we actually see a rather surprising behavior where the tunneling current with exactly the same tip bias can sometimes be positive, sometimes be negative. So it can switch its sign depending on where your tip is. So it turns out this can be understood from the fact that the excited state will actually give rise to a charge transfer exciton where the electron and the hole are sitting at different positions. So when you bring your tip to be above the hole will preferentially tunnel into the tip and give you a positive current. But if you just if you just move the tip a little bit to the position where the electron is localized at, then the electron will tunnel into your tip and give you a negative photocurrent. So that basically tells us that indeed for these excited electron hole pairs, the electron and hole are indeed in that system are sitting at different positions. So the last question we would like to ask is, what will happen if you put many electrons inside a single deep moiré potential? Okay, so in that case, well, we can think this is not a hydrogen atom anymore. Instead, we have like multi-electron atom inside a single unit cell. So in natural atom, we know that all the ordering of the electrons are mostly determined by single particle levels. So they feel 1s, 2s, and 2p, so on and so forth. And then electron-electron interaction can be treated perturbatively. But in a moiré superlattice, the competition between single particle level and the electron Coulomb interaction can be rather different. So, for example, if the moiré potential give a very far separated single particle level, then you would imagine that the particle ordering will be largely determined by the, again, filling the quantum levels of individual potential, and then Coulomb interaction will add some perturbation. On the other hand, if the Coulomb potential completely dominates, is much larger than single particle level separation, then the electrons don't care about what's the 1s and the 2s state anymore. Instead, they just want to be away from each other, and they actually form a Wigner molecule within an individual unit cell. So again, to see what happens in a real material, we turn to the twisted bilayer WS2, which has a particularly deep potential well, so we can add many electrons inside a single, basically, moiré site. And this is basically look at the distribution of holes. So if we put one hole per moiré superlattice, basically we see it is very well localized at a specific position. And when we look at two holes per moiré site, we actually found the electron wave function change rather dramatically. They actually give rise to this ring type of behavior. And if we put three holes per site, we can see the configuration become completely different. It actually shows a very nicely distributed triangles. And this behavior can be understood quite well theoretically by Liang Fu and his students. So these basically 2 electron and 3 electron states are basically Wigner molecules, where when you have 2 holes per lattice site, in classical regime, the holes just want to be away from each other. There are 3 equivalent distributions, but quantum mechanically, or they can mix with each other, and as a result, you will get something behavior more like a ring, and that's comparable to what we see experimentally. And for 3 holes per atom, basically if they want to be fully apart from each other, they basically form this triangle lattice. So individual unit cell, you basically get a Wigner molecule, but then when you look at the large distribution of the moiré system, it actually forms a crystal of this Wigner molecule. So it will be rather very interesting to see how the transport behavior as well as spin behavior can emerge from this periodical lattice of like electron molecules. So, in addition to holes, we can look at how things change when you look at the electrons. So electron distribution, again, with 1 electron, 2 electron, 3 electron, we can see the formation of the Wigner molecule, except in this case, the interaction effect is a little bit weaker. So as you can see, the Wigner molecule for 3 electrons are a little bit blurred compared with holes. And that's because the effective mass and the effective potential for electron hole can be a little bit different. We can further see how these things change when you change size of the moiré superlattice. If the moiré superlattice becomes smaller, what you can see, the Wigner molecule actually becomes less obvious due to the change of the competition between Coulomb interaction and single particle energy. And when you add strain, you can actually very strongly distort these electron lattices. And so basically, they are highly tunable, and then they can behave in many different ways. With that, I would like to summarize. So I think the moiré superlattice can be actually very rich when you look at beyond 1 electron per lattice site, when you consider the effect of the kind of more realistic moiré potentials. And then this work are very close collaboration with Mike Cromie's group, as well as Alex Zetto and Steve Lewis' group at Berkeley. And a lot of the theory is in collaboration with Liang Fu's group at MIT. And the student who did most of the work are Hong Yuan and Ziyu, and postdoc meeting Louis. And thank you for your attention.